Hello, my name is Jeremy Kim and I'll be presenting D-RaNGe, a mechanism that uses commodity DRAM devices to generate true random numbers with low latency and high throughput. To begin, I'll give a brief overview. Our motivation is that high throughput true random numbers enable system security and various randomized algorithms. Unfortunately, many systems like IoT, mobile, and embedded systems do not have dedicated true random number generator hardware. However, they do have DRAM devices on which a few recent papers have proposed generating true random numbers on. The problem is that current DRAM-based TRNGs either do not sample a fundamentally non-deterministic entropy source, which may not result in true random numbers, or they are too slow for continuous high-throughput operation. Our goal is to develop a novel and effective TRNG for existing commodity DRAM devices that can provide continuous high-throughput random values at low latency while minimally affecting concurrently running applications. We propose D-RaNGe, a high-throughput TRNG that reduces DRAM access latency below reliable values and exploits DRAM cell failure probabilities to quickly generate random numbers. In our evaluation, we experimentally characterized 282 real LPDDR4 DRAM devices and find that D-RaNGe provides random values at over 700 megabits per second, which is orders of magnitude over prior DRAM-based TRNGs. In addition, D-RaNGe can provide 64 bits of random data in 100 nanoseconds, which is 180x faster than prior proposals. Here's the outline for the talk today. I will first discuss the motivation of the work. High-throughput true random numbers are required for many real-world applications. These applications include cryptography for securely encrypting file systems, network packets, data in standard protocols such as TLS, SSL, RSA. Others include randomized algorithms, scientific simulation, statistical sampling, industrial testing, recreational entertainment. True random numbers can only be generated from physical processes such as shot noise, electrical noise, thermal noise, radioactive decay, Brownian motion. For this reason, systems generally rely on dedicated TRNG hardware that samples non-deterministic random variables that are inherent in various physical phenomena. Unfortunately, smaller devices such as IoT, mobile, or embedded devices that may not have the provisions for dedicated true random number generator or TRNG hardware require a high-throughput TRNG to enable the previously mentioned applications. However, DRAM devices are available on most systems. A TRNG that generates true random numbers using DRAM would enable applications that require true random numbers to now run on most systems and other applications and use cases. One example would be processing in memory applications, generating true random numbers within memory itself. Our goal is to therefore provide a TRNG that uses DRAM devices and satisfies the characteristics of an effective TRNG. I will discuss these characteristics next. We identify 6 effective TRNG characteristics that we want our proposal to satisfy. It would have a low implementation cost, a mechanism that requires little or no changes to current systems and minimal additional area overhead. It should be fully non-deterministic, which can be guaranteed by sampling a truly random physical phenomena, so it is impossible to predict the next output given complete information about how the mechanism operates. It should provide a continuous stream of true random numbers with high throughput, such that applications are not bottlenecked by the true random number generator. It should provide true random numbers with low latency, such that applications do not have to stall when requesting random values. It should exhibit low system interference, which means that it should not significantly slow down concurrently running applications. And finally, it should generate random values with low energy overhead. I will now discuss our mechanism D-RaNGe after providing the necessary background on DRAM. Each DRAM bank is hierarchically organized into subarrays. Each circle in the cartoon represents a single DRAM cell. Columns of DRAM cells in a subarray are connected with a wire referred to as a local bit line, and rows of a DRAM cell are connected with a wire referred to as a word line, and a row of DRAM cells is called a DRAM row. At the peripherals of the core cell array are a local row decoder, which selects the row to read and write to, and a local row buffer, which amplifies the data that is stored in the cell to an IO-readable value. DRAM is comprised of many subarrays, which are often composed of 512 to 1024 rows. Further peripherals exist containing groups of subarrays called a bank. The global row decoder selects the local row decoder that will drive the word line, and global row buffer aids in the transfer of data to and from the CPU. A DRAM device is comprised of several banks, and each bank can be accessed independently. Let's take a look at how DRAM operates in the scope of a single subarray. Because memory controllers typically access DRAM at the granularity of a cache line, we combine consecutive aligned DRAM cells as cache lines in our diagram. First, we activate the first row, which copies the entire row's data into the row buffer. At this point, we can read our data at the granularity of the cache lines within the activated or opened row. When we want to access data on another row, we must first pre-charge the currently opened row, which prepares the row buffer for copying data from another row. We can now activate the second row before reading data from it. Now let's take a deeper look at the circuitry to understand access latency failures. A DRAM cell holds its data as charge in a capacitor, and the access transistor gates reads and writes to the cell data. The data gets read out by sense amplifier via the bit line when the access transistor is enabled. Initially, the bit line is kept at VDD/2. When the word line is driven high or activated, the capacitor begins to share charge with the bit line. The sense amplifier is then enabled, and the voltage differential on the bit line is amplified to an IO-readable value. In order to ensure correctness of operation, the memory controller can only read data TRCD time after the activation. We could read this data earlier when it reaches a readable voltage threshold Vmin, but we want to make sure that there is enough guard band such that other cells that may be weaker due to process variation will not fail when accessed TRCD time after activation. We highlight and refer to varying degrees of strengths of cells in terms of how early they reach the readable voltage threshold. If we are to read with the TRCD reduced below manufacturer recommended values, we begin to induce latency failures in the weaker cells. Cells that are read when their bit line's voltage is lower than Vmin have a probability of failure, and this probability increases as you read further below the voltage threshold. This leads us to our key idea. Our key idea is to reduce DRAM read access latency below the reliable datasheet specification values using software-only system calls in order to exploit the resulting error patterns as true random numbers. We find that the probability that a cell will result in a latency failure due to a reduced TRC access is inherently related to random process variation from manufacturing. This knowledge enables us to provide random values by observing DRAM cells' latency failure probabilities. Here's a cartoon showing the manufacturing variation across a region of DRAM. When accessed with a reduced timing parameter, some cells have a high percentage chance of failing, while others have a low percentage chance of failing. The key idea is to extract random values by sampling those DRAM cells that fail truly randomly and using the resulting data as random data. We first identify all DRAM cells that fail randomly when accessed with a reduced TRCD, and we refer to these as the RNG cells. When accessing an RNG cell with a reduced TRCD, the values will be truly random, and we can use these directly as output as such. We find that when we reduce TRCD by 45%, we can quickly generate random numbers from RNG cells. To identify RNG cells, we first extract 1 million values that we will refer to as a bit stream from each DRAM cell. We then classify each DRAM cell whose output passes the NIST statistical test suite for randomness as RNG cells. The NIST test suite includes tests for unbiased outputs of 1s and 0s across the entire bit stream, unbiased outputs within smaller segments of the bit stream, a limited number of uninterrupted sequences of identical bits, and etc. To maximize the bits that are accessed immediately following an activation, we alternate accesses to distinct rows in a bank. This access pattern quickly generates TRCD failures within cache lines in 2 rows. This maximizes the TRCD failures when accessing with a reduced TRCD. We first activate the first word line and immediately read the cache line from the first row. We then activate the second word line and then immediately read the cache line from the second row. And we keep alternating accesses to different rows such that we are generating TRCD failures very quickly. Because only cache lines immediately read after activation result in failures, cache lines containing more RNG cells provide more random bits of data per access. To minimize the system interference of D-RaNGe, we give the D-RaNGe exclusive access to RNG cells such that data must not be migrated before starting to generate random values. Here we show a DRAM array of cache lines. We highlight 2 cache lines in distinct rows with the most number of RNG cells in this bank. In order to minimize interference, we reserve these rows such that D-RaNGe can exclusively access the cache lines containing the most RNG cells. We also reserve the surrounding rows such that DRAM data pattern or read-write interference does not occur. We can parallelize accesses across all available DRAM banks for higher throughput of random values. One such example implementation of D-RaNGe is such that the memory controller reserves rows containing the selected RNG cells and neighboring rows in each bank to avoid DRAM read-write interference. When the system is not accessing memory, the memory controller runs firmware that generates random values using the D-RaNGe access pattern. The memory controller maintains a buffer of random data, and D-RaNGe stores the random numbers in the memory buffer at the memory controller. We then expose an API for returning random values from the buffer whenever requested by the user. I will next discuss the methodology for testing DRAM and evaluating our mechanism. The infrastructure we developed can test 282 state-of-the-art LPDDR4 DRAM chips. Each device is 2 GB in size, and we have chips from across 3 major DRAM manufacturers. We test within a thermally controlled chamber with an ambient temperature range of 40 to 55 degrees Celsius with a tolerance of 0.25 degrees Celsius. DRAM temperature is always held at 15 degrees Celsius above ambient using a local heat source. We had precise control over DRAM commands and timing parameters, and we test reduced latency effects by reducing the TRC parameter. We use a cycle-level simulator called Ramulator using spec CPU 2006 workloads simulating a 4-core system to evaluate the throughput, latency, and system interference of D-RaNGe. We also use DRAM power to estimate the DRAM energy consumption of D-RaNGe using the output from Ramulator. I will now go into our results. So how do we know whether D-RaNGe provides truly random values? We test many bit streams with the NIST statistical test suite for randomness and show that the RNG cells that we sample pass the test. And there are more details that we can find in the paper. I will now discuss our latency results. Latency is related to the density of available RNG cells per cache lines. This plot shows the number of cache lines that we find in each bank containing a certain number of RNG cells, which is on the x-axis. The most we ever observe is 4 RNG cells per cache line. Each point here represents the number of cache lines containing x RNG cells in a single bank. Note that the y-axis has a logarithmic scale. We plot the distribution of points for each x value across many banks as a box and whisker plot. The median is the red line inside the box and represents the 50 percentile point. The box is bounded by quartile 3, or the 75 percentile point, and quartile 1, or the 25 percentile point. The whiskers extend 1.5 times the difference between Q3 and Q1 beyond Q3 and Q1, and any point outside of the whiskers are outliers and shown with X's. We plot the latency distributions for each of the 3 DRAM manufacturers that we test. The manufacturers are labeled A, B, and C. We use these distributions to determine the latency of generating 64 bits of random data. As a maximum latency, we assume that we are accessing cache lines containing only one single RNG cell and also using only one cache line within a single bank. We find the maximum latency to be 960 nanoseconds. To find the minimum empirical latency, we assume that we are accessing cache lines that contain 4 RNG cells and that we parallelize accesses across all available banks. We find the minimum empirical latency to be 100 nanoseconds. I will now present the single-channel TRNG throughput evaluation results. We plot a box and whisker plot again for the throughput. The x-axis sweeps the number of banks that we parallelize D-RaNGe accesses on, and the y-axis plots the TRNG throughput in terms of megabits per second. We determine the throughput using the RNG cell densities found. For each DRAM bank that we use, we select 2 cache lines containing the most number of RNG cells. The throughput is calculated by taking the number of accesses we can make per second to a cache line when generating random numbers, and multiplying that value by the sum of all RNG cells in our selected cache lines. We plot the distributions for all 3 DRAM manufacturers. Because we have only observed between 1 and 4 RNG cells per cache line, there are a limited number of possible throughputs. We find that we can generate true random numbers at least 40 megabits per second when parallelizing D-RaNGe access across all banks. We find that the maximum throughputs for manufacturers A, B, and C are around 180, 180, and 130 megabits per second. When we parallelize across 4 channels of DRAM, which is often available on most systems, D-RaNGe can produce random numbers at a maximum of 717 megabits per second and an average of 435 megabits per second. Now let's take a look at the system interference results. We find that the capacity overhead of D-RaNGe is the 6 DRAM rows per DRAM bank that we must reserve. This includes the 2 rows containing the selected cache lines and the 4 rows surrounding each side of the 2 rows. This is an insignificant capacity overhead of less than 0.1%. D-RaNGe is inherently a flexible mechanism and can adjust its level of interference in a number of ways. One way would be to change the priority at which D-RaNGe accesses are issued compared to regular application DRAM accesses. In trying to show the flexibility of D-RaNGe, we study the spec CPU 2006 workloads in the pessimistic case where D-RaNGe only issues accesses to a DRAM bank when it is idle, such that D-RaNGe has no interference with concurrently running applications. We find that in this case, D-RaNGe can still provide on average 83.1 megabits per second of random data. Next, we will look into the energy consumption of D-RaNGe. We find that D-RaNGe can provide random data at the rate of 4.4 nanojoules per bit, and this was determined by Ramulator and DRAM power. Let me briefly talk about other results that are included in the paper before presenting our comparison of D-RaNGe against prior work. These include the following: LPDDR4 DRAM activation failure characterization, including the spatial distribution, data pattern dependence, temperature effects, and variation over time, how D-RaNGe meets the basic requirements for an effective TRNG, a detailed analysis on the devices of 3 major DRAM manufacturers, and D-RaNGe energy consumption, 64-bit latency and throughput, further discussion on the algorithm for D-RaNGe to effectively generate random values, design considerations for D-RaNGe, D-RaNGe overhead analysis of NIST statistical test suite results, and a detailed comparison against prior work, which I will go into now. The first class of DRAM-based TRNGs is DRAM command scheduling based, the second is DRAM cell charge retention based, and the third is DRAM startup value based. I will start by comparing against the command scheduling based TRNG. In DRAM command scheduling based TRNGs, the randomness source is the time it takes to run a code segment containing many DRAM accesses. The authors claim that the time to complete this code segment is random because the time to access DRAM is unpredictable due to memory conflicts, refresh operations, calibration, etc. The time to complete the code segment is measured and the lower bits of the timer are extracted as random values. The authors show that this proposal can generate random values at 3.4 megabits per second. On the other hand, D-RaNGe produces true random numbers at over 700 megabits per second, which is orders of magnitude higher. Unfortunately, we claim that the randomness source is not truly random, as it does not rely on a physical, non-deterministic phenomena. In fact, it heavily depends on the memory controller implementation as well as concurrently running applications. It also can only provide a very small throughput of true random numbers compared to D-RaNGe. The next prior work I will discuss is the DRAM cell charge retention-based TRNGs, along with some background information. DRAM encodes data in fundamentally leaky capacitors, and here's a simplified diagram of a DRAM cell again. There are a number of leakage paths by which charge can enter or exit the capacitor, and the important thing to note is that stored data can be corrupted if too much charge leaks, which is the same thing as saying if the capacitor voltage degrades too much. Here we have a simplified diagram of the capacitor voltage over time. We see that the voltage decreases over time in an exponential decay. Again, we have our voltage Vmin, under which we can no longer guarantee that we will correctly read the data that was originally stored in the cell. As long as the cell's voltage remains above the line, we consider this a retention success. However, as soon as the voltage drops below Vmin, we consider this a retention failure. We define the length of time that must elapse before a cell experiences a retention failure as the retention time of a cell. Retention-based TRNGs generate random values using data from cells that fail randomly with a refresh interval n. We induce retention failures by disabling refresh for a time longer than the standard 64 milliseconds. Here's a cartoon showing the variation of cell retention times in different colors. When we disable refresh for a time interval n, we see that the charge at different cells leak over time. Some cells leak charge below Vmin, which results in retention failures, but other cells can handle a longer refresh interval without failing. After time n, some cells leak close to Vmin, and it is these cells that fail randomly. We refer to these as RNG cells in this context. The key idea is to extract random values by aggregating values from RNG cells after every increased refresh interval. Unfortunately, DRAM retention-based TRNGs have weaknesses. They generate random values with a high latency. Prior work shows that 40-second net refresh intervals result in 256 random bits of data per 4 megabyte DRAM blocks. On the other hand, D-RaNGe latency is 100 nanoseconds, which is greater than 9 orders of magnitude faster. Second, DRAM cell retention-based TRNGs have low throughput and high DRAM capacity overhead. Retention TRNGs require more capacity overhead for higher throughput. However, when even fully utilizing 32 gigabytes of DRAM, these works can only produce around 0.05 megabits per second. On the other hand, D-RaNGe has 14,000 times higher throughput with a fixed capacity cost. Finally, they have high energy consumption. They consume 6.8 millijoules per bit since they have a very long idle time for waiting for retention failures to occur. On the other hand, D-RaNGe can produce random values at 4.4 nanojoules per bit, which is greater than 7 orders of magnitude lower. Lastly, I will discuss the third class of DRAM-based TRNGs, DRAM startup value-based TRNGs. Prior work exploit the interaction of precharge and row decoder logic and column select lines when a device is powered up to produce random values in some DRAM cells. Prior works propose power cycling DRAM to extract the random data resident in those cells. Unfortunately, these TRNGs come with their own constraints as well. The latency of generating random values depends on a long DRAM power cycle time. While the authors do not evaluate this, there is oftentimes a high latency in power cycling DRAM due to all the initialization and calibration required for reading and writing from DRAM. This mechanism has a high storage cost also, since all data will be lost during the power cycle. Compared to all prior work, D-RaNGe performs better in terms of all the identified characteristics of an effective TRNG. Compared to command scheduling based TRNGs, D-RaNGe actually samples a truly random entropy source and provides random values at significantly higher throughput and lower latency. Compared to retention time based TRNGs, D-RaNGe provides random values at orders of magnitude higher throughput, less energy, and lower latency. Compared to startup value based TRNGs, D-RaNGe can continuously produce random values and likely generate random values with much lower latency and higher throughput. Now let me conclude by giving the summary. Our motivation is that high-throughput true random numbers enable system security and various randomized algorithms. Unfortunately, many systems like IoT, mobile, and embedded systems do not have dedicated true random number generator hardware. However, they do have DRAM devices on which few recent papers have proposed generating true random numbers on. The problem is that current DRAM-based TRNGs either do not sample a fundamentally non-deterministic entropy source, which may not result in true random numbers, or they are too slow for continuous high-throughput operation. Our goal is to develop a novel and effective TRNG for existing commodity DRAM devices that can provide continuous high-throughput random values at low latency while minimally affecting concurrently running applications. We propose D-RaNGe, a high-throughput TRNG that reduces DRAM access latency below reliable values and exploits DRAM cell failure probabilities to quickly generate random values. In our evaluation, we experimentally characterized 282 real LPDDR4 DRAM devices and find that D-RaNGe provides random values at over 700 megabits per second, which is orders of magnitude over prior DRAM-based TRNGs. In addition, D-RaNGe can provide 64 bits of random data in 100 nanoseconds, which is 180 times faster than prior proposals. That concludes my talk. Thank you very much for listening.